Applications of integration, page 2. So we're continuing with the problems we did on the last page, and here they give us another function. I'm not exactly sure what this one graphs like, but it must be something that crosses the x-axis because they only give us one of the x limits and not both. So let's try to graph a few points of this function. So for example, x equals 0. It looks like it's going to be like an asymptote. So there's an asymptote at that goes through the origin. Okay, and then let's see, x equals 1 would be 2 minus 1, which is 1. So 1, 1. That's one of the points. X equals 2 looks like it's going to be kind of a weird number. I won't graph that point. Let's see if there's a nicer one. Let's do x equals 4. X equals 4 is going to be 2 minus 1/2, which is 1.5. Okay, so actually this is going to have like an intersection. I'm thinking that it's going to look kind of like this, okay, and it's going to have an asymptote that goes toward x equals 0, and so there is a x-intercept here. Let's calculate what the x-intercept is going to be. So when is y equals 0 is basically what we want to know. So we'll put 1 divided by square root of x. That's an x, not a b. Okay, and then we'll invert both sides. We'll get square root of x equals 1/2. We'll get x is equal to, we're going to square both sides. We'll get x equal to 1/4. Okay, so when x equals 1/4, then it crosses the x-axis. So we can take the integral from 1/4 to 1, or 4, and then the function is 2 minus 1 over square root of x. Let's write that as like a nicer, something easier to take the integral of. So it would be negative 1/2, right? Dx. And just move this up here. And so the integral of 2 is going to be 2x. The integral of negative 1/2 is going to be x to the 1/2 times 2. And then the negative sign is maintained. So we can take the definite interval of that. We're going to have 4 here, and we're going to have 1/4 here. So if we put 4 in there, we're going to get 8 minus, let's see, 4 to the square root of 4 is going to be 2, so it's minus 2 times 2, which is minus 4. Then we subtract the value of this function when we plug in 1/4. So 2 times 1/4 is 1/2, minus 2 times 1/4 to the half, which is going to be 1/2. 2 times 1/2 is 1, so it's minus 1. So 8 minus 4 is 4. 1/2 minus 1 is negative 1/2. So a minus negative 1/2 is plus 1/2. So the answer is 4.5. Okay, and so basically we were finding the area here in this region. We were going from this point here, the 1/4, x equals 1/4, and all the way to x equals 4. Number 3, find the area enclosed by one arch of the curve y equals cosine 3x and the x-axis. So remember, cosine 3x, cosine in general, it starts at 1 and then it goes down. So if they say one arch of the curve y equals cosine 3x, then we could take the left and the right side here. It's symmetrical about the y-axis, okay? And normally this point here, the x here, would be pi over 2. Pi over 2 is when cosine is 0. But let's see. Instead of being pi over 2, it's going to be something different because it's, 3x instead of cosine x. So it's actually going to be something like pi over 6. When we put pi over 6 in here, the 3x is going to make it pi over 2. Yeah, so like when you put, I don't remember how this works very well anymore, but remember this is like a multiplier of the x when we did transformations, right? And so it's either going to make it 3 times skinnier or 3 times wider. And actually what happens is it makes it 3 times skinnier. So instead of crossing the x-axis at pi over 2, it crosses the x-axis at pi over 6. And so the value here is going to be pi over 6, and the value over here is, of course, going to be negative pi over 6 because it's a mirror image. All right, so now we are going to write out the integral. The integral is going to be from negative pi over 6 to pi over 6, because that's going to be one arch of the curve. And then the inside, we're going to have cosine 3x dx. And the integral of cosine 3x, of course, is going to be sine 3x divided by 3. And, you know, that's just a really good guess. But if you take the derivative, you can check it, see, make sure it works. The derivative of sine 3x, using the chain rule, of course, is cosine 3x times 3. The 3's cancel out, and you're left with exactly cosine 3x. So that works out, right? Now, even if you don't guess it on the first try, that's not a problem. Just guess again. You can guess as many times as you want, and every time you're going to get a little bit better. So let's evaluate this. So if we put positive pi over 6 in there, we're going to get sine of pi over 2, which is 1 over 3. And then if we put a negative pi over 6 in there, we're going to get negative pi over, sine of negative pi over 2, which is also, it's going to be negative 1 instead of positive 1. So it's going to be negative 1/3. So 1/3 minus a negative third is going to be 2/3. Isn't that a nice round number? Look at that. If you find the area underneath an arch of a sine or cosine, you're going to get an area that, even though it's all curved and everything, it's going to be a nice round number like that. And like, if it wasn't smashed by a factor of 3, you would probably have a really nice round number like 2 or something like that. Number 4, write down an expression for the area of each region described by the following boundaries. Use technology to calculate the area. Oh, okay, so now this is going to be super easy, right? So we're going to calculate the area under the log x curve. The bottom part of the area is going to be the x-axis, and then the vertical limits are x equals 1 and x equals 4. So if you haven't done this before, the first thing you need to do is you need to program this function, natural log of x, into the y screen. So let's do that. We're going to put here a natural log of x. Okay, and then we're going to do second calc integral. Ooh, it's kind of slow. Okay, so it finally came back. Then it asks me what the lower and the upper limits are. The lower limit and the upper limit are going to be 1 and 4. So first we put 1, and then we put 4. Okay. And the answer gives us is 2.55. Okay. Next one. Now we have a very weird-looking function. So we're going to go in here and we're going to change the log x. I'm going to move this over here. Okay, so I typed in x squared e to the negative x. Make sure that this negative here is using this button and not the subtract button. And then we're going to do second calc integrate, which is option 7. And then we're going to give it the limits x equals 0 and x equals 2.8. So the lower limit is x equals 0. And the upper limit is going to be 2.8. And it tells us the answer is 1.06. Okay, and it even shows you a little graph of it. Let's zoom in a little bit. We'll do like zoom standard. So the part that we're integrating is this part here. So it's just like a little, it looks kind of like this on the right side of the origin. All right. 19b, the area between two functions. So up until now, we've always been doing like areas that are between a given function, like that, and the x-axis, like that. Now, they are giving us two functions, like this function, and then they're also giving us like this function, and basically they're saying, okay, now let's find the area in between the functions. It's a little bit harder. So it says write two integral expressions to calculate the area between the two curves, one using f of x and g of x, and the other using yu and yl. Okay, so the first part of the integrals are going to look the same. It's going to be the integral from a to b, just like we did last time. And in between, instead of just putting f of x, now we're going to put something like f of x minus g of x. Okay, because if we put f of x minus g of x, then it's going to be this line minus this line, and then that'll give us the height between the functions. Okay, and then the other alternative would be using the y's. So then we would say, oh, the upper y minus the lower y dx. So those are the two integral functions you can use to find the area between two curves. Now write an integral expression that calculates the area between the curves f of x and g of x that works even if f of x is only sometimes greater than g of x. So like in this function here, between a and b, g of x is always greater than, or f of x is always greater than g of x, so we can write this without fear that suddenly f of x minus g of x is going to become negative. But if we cannot guarantee that f of x is always greater, if we just write that expression, sometimes we're going to get a negative number, and then part of the area is going to be positive, part of it's going to be negative. They're going to cancel each other out, and you're not going to get exactly what you wanted. So to do that, what we're going to do is we're going to put in a modulus, or like an absolute value, and then we'll say, oh, we're always taking the positive. If there's a negative number that comes out of here, we're going to take the positive of it before we take the integral. And then it's going to be okay. Okay, then if we put the modulus or the absolute value there, it doesn't matter if f of x is sometimes below g of x. It's going to give a negative number, and then we're going to find the positive of it. Number 1a, find the exact value of the area bounded by the x-axis and x squared plus x minus 2. Now they didn't give us the a and b this time, the left and the right limits, and that's because since they gave us this quadratic, we can figure out what the x-intercepts are by factoring, and it's going to be something like this. I think it's x plus 2, x minus 1, right? So one of the roots is negative 2, the other root is positive 1. So when we take our integral, we're going to take our integral from negative 2 to positive 1, and the function is going to be x squared plus x minus 2. Okay? And then the integral of this is going to be x cubed divided by 3 plus x squared divided by 2 minus 2x, and then we can evaluate it from negative 2 to 1. If we put 1 in here, we're going to get 1/3 plus 1/2 minus 2. If we put negative 2 in here, we're going to subtract the negative 2, substitute with 1. It's going to be negative 8/3 plus 2. And then negative 2 times negative 2 is plus 4. Okay. So this is going to give us 1/3 plus 1/2 is 5/6 minus 2. plus 8/3 minus 2 minus 4. Okay, so minus 2 minus 2 minus 4 gives us minus 8. 5/6 plus 8/3. Well, let's see. 8/3 is actually, it's going to be 16/6. So 5/6 plus 16/6 is 21/6. 21/6 minus 8. Yuck, huh? So 8 is, if we put it, if we make a common denominator 6, it's going to be 48/6. So 21 minus 48 is 27/6, something like that. I think it's negative 27/6, right? I know, like, you guys remember fraction, addition, and subtraction, and fraction, subtraction, and addition perfectly, so that was just fine with you, right? And it's good review for the vestibular. So that was the end of page 2.